Hello everyone. In this presentation we are going to discuss about the infinite impulse response filters, and I am Manimegle L, Assistant Professor ECE from R.M.K College of Engineering and Technology. So the contents of the presentation are Iir filters and the realization of Iir filters. Here we are going to see only the two types of realization structure of Iir. One is direct from 1 and another one is direct from 2 structure. So Iir filter. IIR in the sense infinite impulse response filters, which means the impulse response of this filter will be of infinite duration. So consider this hd of e power j omega is the frequency response. If we convert this into time domain, which is hd of n, this hd of n will be of infinite duration. So we can say this hd of n is the dt signal in the range of minus infinite to plus infinite. Then the Iir filters are recursive filters. So recursive filters in the sense the output of any Iir filter is the function of the present input, the past input samples and the past output samples. We can see the given two examples in here. The first example, you can see y of n is equal to 3 into x of n minus 2 plus x of n minus 3 into y of n minus 1 plus 5 into y of n minus 2. Here you can find y of n is the current output, that is equivalent to the function of the present input, which is x of n, and the past input, which is x of n minus 2, and the past output samples are y of n minus 1 and y of n minus 2. Similarly, if you look into the second example, you can see this y of n is equal to x of n minus 1 minus 2 x of n plus 2 y of n minus 1. Here you can see this x of n and x of n minus 1 are the present input and past input samples respectively, and this y of n minus 1 is the past output sample. Representation of Iir filters. The Iir filters are represented with the help of a difference equation. So the difference equation is given by summation k extending from 0 to n ak into y of n minus k, that is equal to summation extending from k is equal to 0 to m bk into x of n minus k. Here y of n minus k and x of n minus k are the output and input variables, and ak and bk are the coefficients of output and input respectively. In alternate equivalent form, it is represented as, on the left hand side it is written as y of n minus summation extending from k is equal to 1 to n ak into y of n minus k equal to, on the right hand side, summation extending from k is equal to 0 to m bk into x of n minus k. And we can express the transfer function of the Iir filters with h of z, that is the ratio of the output by input. So h of z is equal to y of z by x of z equal to summation extending from k is equal to 1 to m bk into z power minus k, and at the denominator it is 1 plus summation extending from k is equal to 1 to n ak into z power minus k. Realization of Iir filters. We can use the difference equation for realizing the Iir filter, that is y of n minus summation extending from k equal to 1 to n ak into y of n minus k represents the entire output terms, and this right side expression, that is k is equal to 0 to m bk into x of n minus k, represent the entire input expression. So if you expand this summation, we'll be getting the equation as y of n minus a1 into y of n minus 1 minus a2 into y of n minus 2 minus a3 into y of n minus 3, so on up to an into y of n minus n, that is equal to b0 into x of n plus b1 into x of n minus 1 plus b2 into x of n minus 2, so on up to bk into x of n minus m. So we have already seen we can use two different structure for Iir realization. First, we are going to see about the direct form 1. So considering the equation to be of second order, which means the summation will be extending from k equal to 0 to 2. We can write the equation as y of n is equal to minus a1 into y of n minus 1 minus a2 into y of n minus 2 plus b0 into x of n plus b1 into x of n minus 1 plus b2 into x of n minus 2. Here this y of n is the output expression, and we can split the output expression into two terms, that is we can rewrite the expression as y of n is equal to v of n minus a1 into y of n minus 1 minus a2 into y of n minus 2. That Vn is given by Vn is equal to b0 into x of n plus b1 into x of n minus 1 plus b2 into x of n minus 2. So this Vn is used for representing the entire input equation. So we can realize the structure for the input terms alone. So we have Vn is equal to b0 into x of n plus b1 into x of n minus 1 plus b2 into x of n minus 2. So considering this Vn equation as the system 1, here we have x of n and x of n minus 1 and x of n minus 2. So we'll be having two delays. X has two terms with a delay, which is x of n minus 1 and x of n minus 2. So 2 z inverse can be used for representing these two delays, and we have three summing blocks, summers, to add the three terms. So we can form the block with the input as x of n and the output as v of n. So the coefficients are b0, b1 and b2. So b0, b1 and b2 are the coefficients of input, which is traveling from the input to output in the forward direction. So this is how we are going to implement the structure with two delays and three summers. We can get the output and the coefficients traveling from the input to output. And the second system, that is y of n, can be represented as y of n is equal to v of n minus a1 into y of n minus 1 minus a2 into y of n minus 2. So in here we can find this y of n minus 1 and y of n minus 2 are represented with two delay elements. So for n minus 1, one delay element, that is first z inverse, and y of n minus 2, the second delay element, the other z inverse. The coefficients are minus a1 and minus a2, which means these are flowing from the output to input. So it is in the opposite direction. This minus a1 and minus a2 will be of opposite direction with the summers. And combining these two blocks, this x of n and v of n as a first system, and v of n and y of n as the second system, and combining these two realization will be getting the direct form 1 structure. So the direct form 1 structure will have separate delays for the input coefficient and the output coefficients. So you can see here this y of n is the overall second order difference equation for the system that has been realized with the direct form 1 structure. And in direct form 2 structure, the same principle is applied, where we have this the coefficients of the inputs b0, b1 and b2 are flowing from the input to the output, and a1, a2 are flowing from output to the input in opposite direction. We can combine this delay and form a single structure for the system 2 and system 1 given by this structure. The coefficients of output y of n phasing from the output to the input, and the coefficients of x of n away from the input to the output. So you can see the unified delay structures here. With this as consideration, we are going to implement the direct form 1 and direct form 2 structure for the given output equation. Here this y of n is given as 4 by 3 into x of n minus x of n minus 1 plus 2 by 3 into x of n minus 2 plus 2 by 3 into y of n minus 1 minus 1 by 3 into y of n minus 2. The direct form 1 structure, we can separate the given equation into two different terms. So one is represented as v of n and another one is y of n. So v of n will be consisting of the coefficients of input and input equation alone. So the input equation will be having the terms 4 by 3 x of n minus x of n minus 1 plus 2 by 3 into x of n minus 2. So here the b0 is 4 by 3 and b1 is minus 1 and b2 is 2 by 3. So replacing b0, b1 and b2 along with the here we have x of n minus 1 and x of n minus 2. Two delays are required, that is we can go for two z inverse terms, and the summing will be done by the three summers. So you can find the system 1 implementation with the help of v of n equation and with the coefficients of the inputs alone. And the other equation is y of n, which is equal to v of n plus 2 by 3 into y of n minus 1 minus 1 by 3 into y of n minus 2. In here you can see the a1 value is 2 by 3 and a2 value is minus 1 by 3. So that is represented with this system 2 realization structure, and we'll have y of n minus 1 and y of n minus 2, which requires two delays, that is two Z inverse blocks to represent. So this is the system to direct form 1 structure. Combining the system 1 and system 2, we'll be getting the overall direct form 1 structure for the given y of n. So here you can see that structure where 4 by 3, minus 1 and 2 by 3 are the coefficients of the input, and 2 by 3 and minus 1 by 3 are the coefficient of the output. And then we can now go for the direct form 2 structure. In direct form 2 structure, the same thing happens, which means you have to divide the given equations as v of n and y of n. V of n consisting of the input variable alone. So v of n is equal to 4 by 3 into x of n minus x of n minus 1 plus 2 by 3 into x of n minus 2. And y of n is equal to the equation v of n plus 2 by 3 into y of n minus 1 minus 1 by 3 into y of n minus 2. So here both the equations requires two delays, as like we have designed for direct form 1 structure. The same is used here. The coefficients of the output is 2 by 3 and minus 1 by 3, and the coefficient of the input, that is B0, B1 and B2 are represented here. It is moving from the input to the output, and A1 and A2 are away from the output. So system, in other words, we can say that system 1 and 2 are getting interchanged in direct form 2, and if we combine these delays together, we'll be getting the direct form 2 structure. So the overall direct form 2 structure we can see. So here is the overall direct form 2 structure. So we have combined the delays together. So two unit delays, that is first Z inverse and the second Z inverse, and the coefficients of the output equations are here, and the coefficient of the input equation is here. The summing blocks and the overall input being x of n, and the overall output is being y of n. Finally, in this presentation, we have seen what is an Iir filter and the representation of Iir filter and the various type of realization of Iir filters. Thank you.